Okay, lesson 101, the first lesson of the year here. One of the things I want to work on is just recognizing some basic electrical terms. Okay, we really have four big terms that we need to be very familiar with. And one of the things we're going to do to help understand these is I like to use a water analogy or relate these terms instead of electricity, something we're all a little more familiar with. Let's relate them to water instead, right? So the four terms we have to worry about: number one, voltage; number two, ampacity; number three, wattage; and number four, resistance. Okay, so let's kind of break down and go into the first term here, voltage. So if we're going to use the water analogy, it's equivalent to water pressure, or pounds per square inch. So how hard is that water, sort of pushing through that pipe? Well, how hard is that electricity pushing through that wire? How much electrical pressure, so to speak, are we dealing with? Okay, so the unit of measure for that is volts, or abbreviated the letter V. Every one of these terms kind of has a second abbreviation, for lack of a better term. So they consider voltage to actually be what they call electromotive force. All right, what does that mean? Not terribly important. However, that letter E, you're going to see it abbreviated quite often in the textbook and in formulas as the letter E. So we also need to get familiar. If we see the letter E, we're still talking about voltage. You're going to have to, in your own mind, let those become one and the same. You need to use each pretty interchangeably because you're going to see it both ways quite often. Okay. And voltage can be AC or DC. You'll read a little more about specifically what that means in the text. So our next term, our second term, is ampacity. So that's going to be equivalent to volume. Okay, so gallons, if you want to use that as a unit of measure, if we're going to equate it to water. So if you were going to, fill up a container full of electricity, how do you measure that? Well, we would measure that volume in ampacity. All right. So again, the unit of measure is amperes, more commonly called amps, abbreviated by the letter A. And again, you're going to sort of see that second abbreviation. They consider ampacity also intensity. So because of that, you'll see it abbreviated by the letter I. Again, get used to seeing A or I used interchangeably to represent ampacity in a formula or in a text. Okay, our next term, our third term, is wattage. This one's a little bit different than the first two. So wattage measures the amount of work that's being done by a circuit. Okay, so how do we equate that to the water analogy? I'll show you in a minute here. I got a couple videos, but the unit of measure for that is watts, abbreviated by W, of course, no surprise there. Our sort of other term, power, they consider this to be power because of that, the abbreviation. You'll see the letter P. So again, W or P, we're talking about watts. You got to get familiar with both of those as well. So I mentioned wattage is a little different than the first two. Wattage doesn't really stand on its own. Mathematically, it is made up by volts times amps. Okay, so wattage is the one formula that really depends on the combination of volts and amps, and I'll explain that just a little bit more here in a moment and in a lot of future chapters too. But let's go back to that water analogy. So I have two videos we're going to look at. So on both of these, I want you to think about relative to one another. What is the pressure, the water pressure like, and what is the amount of water, the volume of water like in either of these two scenarios. So keep that in mind. So first one here, guy at a fire hydrant. Okay, fire hydrant here. Let's see what happens. Not a good scenario. That thing blew the guy way back, right? All right, so next one. Okay, totally different here again. But we essentially, what I want you to think about is both these situations have achieved the same amount of work. Because remember, wattage is the measure of work, electrical work being done, right? So let's think about that. In the first situation, the fire hydrant, we had pretty high pressure and compared to the swimming pool, pretty low volume, right? And the opposite side of that is we had on the swimming pool, low pressure, but a lot of water, high volume. And they both did the same amount of work, okay? The same thing can be said for electricity. Because now if we're talking about voltage instead of pressure, we're talking about amperage instead of volume. We can have a high voltage and a relatively lower amperage could do the exact same work as a lower voltage and a higher amperage. Because again, as I said, wattage is volts times amps mathematically. And we'll really dive into that topic in some future chapters here and throughout the year. But for now, as an introduction, we need to sort of put a pin in that one and just wrap our mind around that general idea. Okay. So the fourth term we want to talk about is resistance. This one, in my opinion, is really different from the other three. And I'll hit that in a minute. But if we're going to use the water analogy, maybe if you want to use pipe size, okay, because resistance is the opposition to electrical flow, okay. So a bigger pipe would let more water flow, a smaller pipe would let less water. And the same thing can be said for wires. Now, there's other factors besides size that affect resistance, but again, we'll talk about those in great depth as well. So we're going to measure that one in ohms is our unit of measurement. So this is your omega symbol, really, but the ohm symbol. So get used to seeing that. And then naturally resistance. This one, they kind of flip-flop the terms. You're more familiar with R as the term, but this is the actual unit of measurement, the ohm symbol. What we call it resistance or R. So once again, you could see the ohm symbol, you could see the letter R, interchangeable. We have to get used to both. And the reason I said resistance is different than the other three, this one's really, it's a property of the conductive materials of the circuit. It has nothing to do with the amount of electricity or anything like that. It's really irrelevant of all of those. This is just a property of the conductive bodies themselves, right? So I'm going to hit you with a little bit of just a quick review of everything we threw out there. If you're going to take anything away, let it be this one slide. This will take you pretty far in this curriculum. So the first term we talked about was voltage, abbreviated by the letter V. We're going to equate that to pressure. If we're going to use the water analogy. It's also known as electromotive force, or abbreviated with the letter E. So voltage is going to be V or E, right? Ampacity, abbreviated by the letter A, oftentimes simply referred to as amps, is an amount of electricity, of current, abbreviated by the letter I, which stands for intensity. And then we have wattage, abbreviated by W. That's a measure of electrical work, and we refer to that as power. So P, it can also be abbreviated by the letter P. And lastly, we have resistance, represented by the ohm symbol. And that's actually a property of the conductor itself. It's the conductor's opposition to electrical flow, right? And we're going to abbreviate that also by the letter R, naturally stands for resistance. So, voltage, you could see V, you could see E. Ampacity, you might see A, you might see I. Wattage, you see W or P. And then resistance is the ohm symbol or the letter R. Again, take a mental snapshot of this slide. You can pull a lot of info for just about every lesson we do right from this view right here. All right.